one of the practical methods that is uses a set of data consists of images to extract some useful information, for example, recognizing patterns or detecting an object of interest, is deep learning. So what is deep learning? Well, deep learning is one of the machine learning algorithms that uses an artificial neurals that that is connected between each other to recognize or to extract some patterns and make decisions. Of course, these neurons, we have to construct them. However, we don't have to explicitly program every one of them. The tuning this neural network is a process in which we call training. So how do we tune these neural network? Well, every neural network is simply a value holder. Every neural will have a simple value, only a value, and these values will be pass on the value, its value, to the next neural network or the connected neural network. As it passes through this neural network, it will be multiplied by weight and will be summed by a value called bias. We don't control directly the value of the neural network or the actual neuron. However, we directly control the weight of this that is going to be multiplied in order to pass on to the other neural, and we actually control the bias, in which simply the summation added to the weight multiplied the value of this neuron. So how it looks like? Well, if we have a data with an input value, for example, x1, x2, x3, x4, and a target value of, let's say we try to classify something, so it's 0 or 1, we simply add these ones to be, every value will be x1, x2, x3, and x4 as an input layer of specific values, and these values will be passed on to some layers here, we call it hidden layers, and after that, of course, depending on the architecture, will be passed on to the resulting layers, which is in this case the output layers of 0 and 1. The hidden layers will get its value from the input layer, and after we start initializing these weights and biases, after we initialize it, we will have it checked if it's going to provide us the 0 and 1 we want, or there will be some error. The error, we call it in this this analogy, is we call it loss. And based on this loss, we will update our weights and biases until we get as good as possible or as near as possible value for 0 and 1 for the data we have. Now, as we said, we will multiply every neural network value with the weight, and we sum it with the bias, and we will pass it into a function. These functions, we call it activation functions. And in our neural networks, we simply we can choose any function we want. However, we need to test some functions in order to get a good answer. One of the most popular functions or activation functions is ReLU function, in which if the value is minus of that neural network, it will just return 0, and if the value is positive, it will return that value. Now, another popular function is sigmoid function, which is, it has this graph that at the end it will provide the output of every neuron is between 0 and 1. As you can see, it is bounded by 0, and here is 1. And another one is leaky ReLU, which is, if we have a minus value, it will provide a very small leaky value, a very small value. This is why we call it leaky ReLU. And if it's positive, it will it will provide the same value. So these functions, however, I would say that the most now commonly used is the ReLU. However, you can see different architectures of neural networks that they use different activation functions. Now, cost functions. Again, as we said, we will have input layer and then output layer. And the output layer is made of values we predicted it, which is based on our weights and biases of the whole network. And we need to compare it with the values that is real values. This is in our training data. We always have cases. We try the input with our already made weights and biases, and then we will compare it with the actual output that we have. And based on that, we will calculate the loss. And the loss in the simplest way is we can use, for example, mean square cost function, which is the same mean squared error we already know from previous lectures. It's as simple as we minus the value we predicted minus our real value, and it's going to be squared. In another value is we call cross entropy cost function, and it has a different formula that is always based on the idea of comparing the actual value or the expected value with the expected value from our network, that is we predicted it based on our input and our current weights and biases of the network, with the actual value of that training data. For example, if we're comparing, if we have an input layer of an image of a dog, and the result was we should be a dog should be 1 and the cat should be 0. If we have not, if we have the opposite, that means the weight has to be updated in order to match this this output, which should give us a dog, because the image is a dog. Now, how do we do that? Like we can understand that in a big network, there is a huge amount of weights and biases. And well, we need to tune it. And the problem with tuning, we need optimizer, because of course we can tune it by ourselves, by our hands, but it's not very practical, and it's I'm not sure if it's even possible. So to do that, we need optimizer, in which we will take these parameters and we try to reduce the loss as much as possible. One of the early and also used optimizers is the gradient descent. And the gradient descent is it's about simple idea, that is we have a function or we have all these parameters, and we need to check these parameters how we can always reduce the loss. And as we reduce the loss, we change our step size. For example, we can start at the beginning a little bit big step sizes, and then we start going smaller as we go. Of course, it's always if we have a bigger step size, we will get to the optimization value quicker. However, if we have too small, if we have too big, that we might never get to the actual value, because we can go from here to here, and we will just miss the minima that we are looking for to reduce the loss. And we cannot also go very small, because simply it will take too much time. So we need to always kind of balance these two things, like the step size. Another maybe more used method is the back propagation. And back propagation is based on the idea of we start with of course we will have in the network with our initial weights and biases, and we start from the output of this network, and we go in the opposite direction. This is what we call back propagation. We start from the back of the network, and we can see the expected value we have, and what is the effect of changing these weights on the expected value we have. Depending on the difference that between what we can change and how we can get closer to these the output value, we will change the weights and biases of the of this network. And after that, we will predict the values of the layer just behind the output layer, and we keep doing the same to the layer behind it and layer behind it and so on until we get to the first layer. So this is basically the idea of back propagation. Of course, we have to do it for a lot of data or patches of data, and with these patches of data, every data depend on the loss value. We will update the weights a little bit more, a little bit smaller, and so on. The overall, we should have a model that will work well for that patch, and then we will get another patch that we tested, and then we update the weight and biases, and so on and so on. So we will, of course, not going to train the data in like as a whole. We will split the data into patches, and these patches will go into the network and we get trained. And with time, we will keep getting closer and closer to the lowest possible loss.